All right, this is where the review left off from last week, where we picked up with section 2.2. A couple of these problems actually could have probably fit into the 2.1 region, but I'm not going to do all of these. They're all the ones that require work or worked out in your course pack, but I'll just kind of take a quick glance at them for you. 27 is one of the more interesting ones because what you're basically dealing with is a step function, right? And we remember step functions, they used to look like, I'm gonna build a specific step for us here because they have the closed dots on the left, because this one has not been reflected through the x-axis, and then open dots on the right. Let's make it, I don't know, blue, I guess. And then we'll put a little open dot on the right just to make sure we know it's an open dot on the right. So normally what we get with these steps, right, is this nice progression of little pieces that go up every integer value. So for example, this is 1 and this is 2 and this is 3 and this is 4. You get a little step uh, at the level of 1, and then the next integer value would jump it up to 2, and then the next integer value would jump it up to 3, right? And every time we get to the next x integer, it jumps up. This 4, however, this 4 is going to change this, and it's going to make these guys go up by 4. So every time we get to the next integer, so like if we reach the number 1 right here, right? Suddenly we're not going up by 1. 4 times 1 is 4. And so the next one would jump up to 8, and that's kind of how it's working. And then with this particular graph, we don't really even care because of what they're asking about. We don't even really care about the positive region. We really we need to go back to -5, right? So we'd kind of be going, so if this guy was here, this guy would be going down 4 for the next one, and this guy would be going down 4. So that's one way that you can evaluate it. It would take a little bit of time, right? Because we're only at -1, -2, -3. So this is only between -3 and -2. I'd have to go 2 more steps down before I realized, and this is the key, that as I'm coming in from the left, I'm at a height of -6, or 6 times 4 is 24, so -24. If this was a plus, and I was coming in from the right, I would be at a height of -20. Okay, uh, you could do it this way. Visually, I think a lot of people would like to see it that way, but it is kind of clunky and it takes a while. So what I would do is I would just think, okay, if I am coming into -5 from the left, what is a value that is just a little bit, below -5? Well, how about -5.1, right? Now, this is where it gets tricky because we have to remember what the greatest integer function really means. It means, by definition, that you take the greatest integer less than or equal to the integer in the function. And a lot of people are going to say the next integer that's less than or equal to -5.1 is -5, but -5 is bigger than -5.1. Okay, as we get smaller, we move to the left, and so the actual answer would be -6 is the next integer less than -5.1, and that's where the answer -24 comes from. I think a lot of people just have forgotten about what that function really means. So you might go back to Unit 1 and review it a little bit. This one is just not a problem at all. I mean, at first you're freaking out because you're like, oh, I probably have a vertical asymptote here. And then you realize, no, the vertical asymptote would happen at -7. This is +7, which means that this rational function, which is continuous everywhere except at its vertical asymptote, will be continuous at 7. So you can just plug 7 in. 7 here, 7 here, 2 times 7. 7 plus 7, they both equal 14, and that's a 1, right? So you just get a 1 for that one. Number 29, You really got to get in the habit of immediately looking at this. I think a lot of people would look at this and start, oh, I have to factor and see if there's vertical asymptotes or holes, blah, blah, blah. But the uh, the infinite limits, the end behavior doesn't care about vertical asymptotes or holes. They just care about whether we're converging or diverging. So what really matters is the power on the top is 2, the power on the bottom is 2. We call that a tie, right? And when there's a tie, the rule is you just look at the coefficients. So this has an end behavior model of 2/5. And what that means is that the limit as we approach positive or negative infinity would be 2/5. This guy right here and this guy right here are interesting because it looks like they're the same problem, but then you realize they're not. This one is approaching 0, which initially it looks like, oh, I can't do it. I can't do this problem because I'm approaching 0, and there's a vertical asymptote there, but it turns out it's really a hole because I get a 0 on the top and a 0 on the bottom. So the trick here is to factor an x out of the denominator and then cancel it with the top, and then you're good to go. And hopefully you looked over this one in the back of the book. This is what it looks like, where you factor out that x, you cancel that x. Now here we split the sign out. We really don't even need to do that. I could just plug the 0 in directly, to this level of the problem. Put a 0 here and a 0 here. Sine of 0 is 0, and 0 minus 1 is -1. 0 divided by -1 is 0. So there you go. There's your answer. Okay. You could also use end behavior analysis to do this. I guess not if it's not approaching the ends, though. We'll do that on 31 here in just a second. Speaking of 31, it's the same exact function as number 30 was, except this time it is end behavior. It is end behavior. We're approaching negative infinity, so left end behavior. And so you could cancel those x's again, and that would work. But it's just as easy to look at the power. The power of this top is x. X is way more powerful than sine of x. The power of the bottom is x squared. When the bottom has more power than the top, the end behavior is always going to go to 0. That's just the rule. So hopefully you're seeing that enough that that's starting to click. Okay. Now there is an algebraic way to confirm that. And here is the work from the back. Okay. Same thing that we did on the other problem where we get rid of those x's, factor and cancel, and then we split it off. Actually, I guess we wouldn't cancel them the way they did it. They kept the x on the bottom to fit with the sine of x on top, because this is an identity. This goes to 0, right? If it was going to 0 here, it would go to 1, but the way that it's going to infinity, it goes to 0. And then here I can just say, oh, the end behavior, since I'm going to infinity, the end behavior is 1/6, right? The x is tie, so we look at the coefficients. 0 times 1/6 is 0. I think, and I hope you agree with me, it's way easier just from the very get-go to look and say it's end behavior and the bottom is stronger than the top. Anytime that happens, your function is going to collapse to 0. If you're struggling with what functions are more powerful than others, I did put together a resource page for you and send it out. And you can find that on there and look it over, and hopefully that helps you a little bit. This is one that's very similar to a problem that we would have done like last week, where we're approaching 0. We can't put a 0 in. Oh, but I could factor a bunch of x's out and cancel them, and then maybe I can put a 0 in. And that's really all you had to do on 32. As you can see, once I get rid of this x right here, there's no problem putting a 0 in anymore. Once I plug the 0 in, I get rid of the limit notation, and I end up with -2/3. 33 is impossible because this function's domain begins at -4. So all x is greater or equal to -4. -6 is not in the domain, so you can't get real numbers around there. It's impossible. It does not exist. These two appear to be dealing with vertical asymptotes. Here, there's a vertical asymptote at 4. I'm approaching it from the left. Here, there's a vertical asymptote at -3. I'm approaching it from the right. With a calculator, these are super easy. You graph it on your calculator, and you look as you approach from the left or the right. Am I going up or down? Because whenever there's a vertical asymptote, your answer is always going to be, it's a one-sided limit. You're approaching positive infinity or negative infinity. That's it. If you don't have a calculator, it gets a little tricky. Now you're at home with a calculator, so you're going to be using your calculator on these if you want. But I'm going to give you just a kind of a little idea of how you would do it if you were stuck without a calculator. Okay, so first of all, we're going to know that there's a vertical asymptote for this guy at 4. Second of all, we got to know which way we're coming into it. We're coming in this way, right? Third of all, I'm going to pick a number that's just a little bit to the right of this since I'm moving in from the left, or I'm sorry, to the left of it since I'm moving in from the left. So how about like 3.9? So 3.9, right? And then I don't need to know values specifically. I just need to know whether they're going to be positive or negative. So when I put a 3.9 in the top, it's a positive number. When I put a 3.9 in the bottom, 3.9 minus 4, right? That's going to give me a negative 0.1, but we don't care about what it is. It's just negative. A positive divided by a negative is negative. No matter how close I get to 4 from this side, the top's going to continue to be positive, and the bottom 4 will be bigger than 3.99 or 3.999. The bottom is going to continue to be negative. What that means is I'm going to get bigger and bigger negative numbers, and it's going towards negative infinity. So that's why the answer for 34 was negative infinity. That's how you can just kind of do a number test to figure out if you're generating positive or negative numbers. Okay, so that's a little hint on how to handle 34 and 35, although you probably just graphed them on your calculator. Then once again, end behavior, right? As I move to the right, we don't usually see the plus with the positive infinity. As I move to the right, what kind of function is the more powerful? Well, negative e to the negative x is a double reflected graph. So that's a graph that was, normally, this is e to the x, right? But e to the negative on the inside, the negative x, right, it's gonna reflect it through the y-axis, and then the other one through the x-axis. This is where those transformations become really important for, that we studied earlier. So this is what negative e to the negative x would work. Now x, on the other hand, we know exactly what x looks like. X looks like this, right? So as we go to the right, which one's more powerful? The one that's collapsing to 0 or the one that's moving up? Well, the one that's moving up. So this is the more powerful one. The bottom's more powerful. This thing's going to go to 0. So I know that was pretty fast moving through all those problems, but hopefully that makes some sense for you. Since that was the vast majority of the problems. The next bunch of problems were just end behavior models, and so you just have to find the key players, this dude and this dude. It's a tie. If the x and 6 cancel, all that's left is the coefficient. So your end behavior model, once you reduce it, will be 2/3. Okay, and if there is a tie, the horizontal asymptote is that end behavior, so 2/3 y equals, right? Horizontal asymptotes are y equals, vertical asymptotes are x equals, so y equals 2/3. Number 38, here's your key player up here, here's your key player down here. This time the bigger power is on the top, so when you finish reducing that end behavior model, 3x to the 6 over x to the 4th, I think you're just going to get 3x squared. Well, if you know your polynomial end behaviors, right, positive even is up, and so that's diverging, right? That's diverging towards positive infinity. That means no horizontal asymptotes. Number 39, we've got an x cubed up here. We've got an x to the 6 down here. Whenever so first of all, the end behavior model would be 4x cubed over 6x to the 6, so 2 over 3x to the 3rd. All right, that's what it would cancel less. You'd have 3x cubed left in the denominator. Whenever the whenever the numerator or the denominator, whenever the denominator is more powerful, when you start looking towards infinity, negative infinity, it's just going to get tinier and tinier. The fractions are going to collapse to zero. So that means your end behavior model is, well, your end behavior model, we said was 2 over 3 um, x to the third, right? But more importantly, the horizontal asymptote is at 0. Okay. Anytime that you have a polygon, just a regular, nice, not a rational function, just a polygon, the lead term, we call that the power, the power function is going to be the end behavior model. Okay. And because that's up end behavior, right, there's going to be no horizontal asymptote. 41. It's a tie again. So the end behavior model is going to be 4 once the x squareds cancel. And the horizontal asymptote is also going to be at 4, isn't it? And then finally, here we have the bottom is more powerful than the top. And so the end behavior model would be 2 over 3x after the x squared over x cubes cancel, right? But when the bottom's more powerful than the top, what happens? The whole thing goes to 0 at the ends, okay? The whole thing goes to 0 as we approach positive or negative infinity. So um, 0 is the horizontal asymptote. So yeah, a bunch of practice on those. On these, we're looking more at vertical asymptotes, and so it's pretty easy to identify where those are going to occur. This one's going to occur at 2, right? This one's going to occur at positive 2. So now the only question becomes, as I come in from the left and as I come in from the right, what direction am I going? I would totally just throw this on your graphing calculator and look. I think that's the easiest way to look at it. However, I just taught you a trick a couple minutes ago that can get you through it. And that trick has to do with testing numbers. So if I put like in a 1.9, right, a little bit to the left, so we're doing the limit of f of x as we approach 2 from the left. Okay, negative means the left. So if I put a 1.9 in, I'm going to get a positive on the top. 1.9 minus 2 is a negative on the bottom. It looks like I'm going to be approaching negative infinity. On the other side, if I go just a little to the right, just a little bit to the right, and take the same limit, whoa, stop. As I approach 2 from the right side, okay, of f of x, 2.1 is positive on top, but 2.1 minus 2 is now positive on the bottom too. So positive divided by positive is positive. And so that's kind of how you could check it without a calculator. But you guys certainly could save yourself a lot of time if you just throw these into your calculator on these. The way that we would normally do these types of problems on a non-calculator quiz, back in the old days, is we would give much more predictable functions. So what I mean by that is instead of 1 over x minus 2, where this x could kind of make things a little weird, we would just give, f of x is equal to like 1 over x plus 4 or something. So we knew that there was a vertical asymptote at negative 4, but because there's nothing fancy about the top, it's really just a simple transformation of the parent function 1 over x. And so if we know that the parent function normally looks like this, right, then all we'd have to do, once we knew that the vertical asymptote was at negative 4, is just go like this. Oh, so coming in from the left, it's going down to negative infinity and positive infinity from the right. So we used to do much simpler problems without calculators. You'll probably would still see something like that. But know how to identify vertical asymptotes by comparing the denominators and numerators once they're factored, and then know how to look at pictures and see what directions they're going. 46 and 47 ask you to look at the end behavior. I know it's end behavior because two things, really. One thing is they're asking me as we approach infinity, and number 2, they're talking about horizontal asymptotes. Those two things go together to imply that we're dealing with end behavior, right? So these are kind of interesting. I mean, this one right here is a situation where you have really just an x over an x, because the square root of x squared really just turns into an x. Don't worry about the 2 because it's weaker than the x, right? Get rid of that. And so x over x is just 1. So you're like, oh, this is just going to have end behavior of 1, like x over x would. However, there's a little bit of a cool thing going on in which as we go to the right, you do get 1, because this is 1 and this is 1. But as you go to the left, like let's take, negative -3, right? When I put a -3 in here, I get -3 squared. It turns into a 9 and turns back into a positive value. Now the 2 makes it a little more than 3, but it's the further out you go, you get closer and closer to the same value you have on the top. The top, on the other hand, doesn't turn back into a positive 3. It stays a -3. So you get a negative over a positive, numbers that are very, very close to each other. And so what you get is a -1, a -1. And this is what the graph looks like right here. And you can see that we do have a horizontal asymptote of +1 as we move to positive infinity. And look at this tail right here as we move to negative infinity, going to -1. So we have two different horizontal asymptotes depending on the direction that we're moving in. Furthermore, this one is a little easier to interpret. We just look and say, oh, look, the bottom is more powerful than the top. That function right there is going to have a horizontal asymptote at 0 in both directions. And just remember how you write a horizontal asymptote using limits. You basically just say the infinite limit, right? So you say the limit as x approaches, and then so if we were going to do to the right, so the right end behavior of f of x here, in this case, is 0. So that indicates that 0 is the horizontal asymptote. And this is the one you submitted. The whole premise here is that if the limit as x approaches positive infinity of your original function divided by its end behavior model equals 1, meaning that these two things are getting closer and closer to being equal, because when you divide things that are the same, you get 1, then we know that g of x is confirmed to be the right end behavior model. If I want the left end behavior model, I just have to go to the left. So I have to go to negative infinity, and it's the same situation. And we did a big example a couple days ago. You did a bunch, 4 problems 2 nights ago, and then one more last night. And this is one I actually asked you to turn in, and it should have looked very similar to the way you've been doing all the others, right? The first thing we do when we take the limit is we determine which one is going to be more powerful in each direction. This is probably the most important part of your problem. So I would take the two parent functions and just kind of get an idea of what I'm looking at. So the e to the x looks like this. The negative 3x is a line with a negative slope, so it probably looks more like this. So it looks like in the right direction, okay, the e to the x is going to be way more powerful. Look at that document that I sent you sometime late last night, early this morning. The most powerful function we have is e to the x. It'll overpower everything. So that's why I've chosen e to the x as my right end behavior model. On the other hand, as we move to the left, right, e to the x is collapsing to 0, whereas negative 3x is moving towards infinity. That's why I chose negative 3x as my stronger function, my end behavior model to the right. That's the most important decision you make. After you make that decision, these are like clockwork, right? You take the limit of the original function divided by the end behavior, you split the function, you split the limit. One of these will always turn into a 1 because you're dividing it by itself. And if we did it correctly, the other one will always, once we take the limit, will always turn into a 0, because the stronger function's on the bottom, and so those fractions are getting tinier and tinier the further out you go. I haven't had anybody ask me specifically to go over these more than what we've already done. So I'm assuming that you are in pretty good shape, but that's the idea there. And then finally, this last problem was just one you had to sketch. This is what your sketch should have looked like. And then you just evaluate, the limits. What am I looking? What am I doing as I move toward 1? We know that because of the breakpoint at 1, we may get some different values. We have a vertical asymptote that the function's coming in from the left with, so we're approaching negative infinity, but from the right, it's just a cubic value, so it just has a value, and 1 cubed is 1 minus 2 times 1 is 2, so now we're at negative 1 plus 5 is 4, so 4 is the limit. Now the other part is to explain, why the limit does or does not exist. And that's where you have to remember, right, these key points, that if a limit, a two-sided limit is going to exist, and that's what this is, right? There's not a plus or minus with the 1, it's just 1. Then the two limits have to agree. And so definitely negative infinity is not even a real number, and it's not equal to 4. And so the left and right limits do not agree. And so there is no limit. And that is the end of the review. So that was fast, but I want to get this out to you so you have an hour or two to do this before you start working on your quizzes today. And I hope you have a good weekend. We will, be talking to you sometime next week. Bye-bye.